So we can use current division for these types of problems here where we're given a source current and then we're given a set of parallel resistances or impedances that are connected to our source, and the current is divided up amongst them depending on the resistances. So in this first example, we're going to derive the current division rule. Just starting with using Ohm's law, there's a voltage across all of these resistors, which is given by Vs. So that voltage, Vs, is going to be equal to our source current times the equivalent resistance of all of these, which we're going to be called RT. And because these resistances are in parallel, RT is going to be equal to 1 over RT is going to be equal to 1 over R1 plus 1 over R2 plus 1 over R3. And then because in these problems we're also given a specific branch current we're looking for, so in this case we're looking for the current through our resistor 1, we can come down here and define that with Ohm's law as well. So the current through R1, R1 is going to be equal to that voltage, Vs, divided by the resistance, R1. And then we just simply do some substitution here. IR1 is equal to IS times RT over R1. And then we can say in general, the current through the resistor of interest or the component of interest is equal to the source current, the current that's being divided amongst the components, times the total resistance of the parallel combination divided by the resistance of the component you're actually interested in. So this is the general formula that we're going to use and that we're going to apply to this example that we've got down here. So we have a current division problem. We've got two meshes, a couple resistors that we can simplify, and we're looking for this current here, Ix, which is the current going through R3, and also R4 as well. So first we can simply combine R3 and R4 in series, and really that's going to take care of all the simplification. Quickly redraw this circuit. It's going to look like something like this. R1, this is still R2, and this is R3 plus R4. So now we see that this combination R3 plus R4 is now in parallel with R2 because they're connected to the same pair of nodes. This is our reference. This is our reference node. So R2 is in parallel with R3 plus R4. So now we can use our current division rule. Because if we come look at the flow of current, IS travels through R1. IS travels through R1 here. This is still IS. But then IS is going to be broken up by a path to ground through R2 and the path to ground through R3 plus R4 here. So that's where the current is being divided. So that's why we don't have any current to divide here dealing with R1. So our source current is going to be 3 amps. So we're looking for Ix. Ix is going to be source current times it's the total resistance. Total resistance we have 1 over RT, 1 over R3 plus R4 plus 1 over R2. So I'm just going to plug these numbers in and get these values real quick. So 1 over is equal. R3 is 10, R4 is 10, so we have 1 over 2 plus R2 is 20 ohms. I'm going to use product over sum for this time. That's right. When you have it like this, you'll just end up with half. It's late, excuse me. So yeah, that's gonna get you just 10 ohms for your total resistance. And then the resistance that we're actually interested in is R3 plus R4, which was 20. So we see that this is gonna be 1/2. So 1/2 of 3, X is just gonna be 1.5 amps. And then I'm gonna quickly double check that. We're not really double check it, but just prove it inside of LT-Spice. Okay, quick little schematic. Two different choices of current sources inside of LT-Spice. I just go for the default current one instead of like the loads or the behavioral sources. Add our reference and our values. It's 3 amps. And R2 is 20. R3, R4 was 10. So we're going to run a DC operating point. And we see that the current through R3 and R4 is 1.5 amps. So that's the answer that we're looking for. Hopefully you guys can see that. And then we're going to come back here and take a look at another more complicated example problem here where we're looking through IX, looking for IX, which is the current through R4 here. So when we have problems like this, we're going to have to do a little bit more simplification just to break the problem down into smaller parts. So immediately we see here that R3 and R4 are in parallel. So even though we eventually just want to find the current going through R4 by itself, we are going to have to do this combination, this parallel combination, because there's 3 paths for the current to take really at this junction. It can take R2, current can go through R3, and then current can also just go through R4. Now, of course, the current from R3 and R4 is going to combine again and go through R5, but those are still just the various paths that the current has to take. So redrawing this circuit, R1 stays the same. Leave R2 for now. We're combining R4 and R3. R5 stays the same. And then we can use this to find the current going through, or really we can use it to find the current going through R2 and then do some subtraction, or we can use it to find the current going through R4 and R3 and then do current division there, which I think I'm actually going to do that way. IS, I'm going to start just writing the values so I don't have to check them later. R2 is 30 ohms. We had R3 and R4. R3 and R4 were both 30 ohms, so this is going to be 15 ohms. R5 was 15 ohms, okay. So, yeah, like I said, I'm going to do current division to find the current going through this combination here, because this 15, we have to remember that this is R3 in parallel with R4, so we can break that back up when we work back. So I'll make another variable, IA, So IA is going to be equal to our source current, which is 10 amps, times RT. Now, our RT is this entire combination. So, quickly say, so we got 1 over 30 plus 1 over 15 plus 15. So that's 1 over 30. So this is just going to be 15. My total current, our total resistance for this combination here, just going to be 15 ohms. And then we're interested in all this. So that's going to be 30. So that's going to be half of 10. So IA is going to be 5 amps. So now we come back up to our original circuit. We know that 5 amps is flowing through, 5 amps is going to be flowing back through this path. So R4, the current through R4 plus R3 adds up to 5 amps when we're coming back here. 5 amps is going through this combination. So now we know we can divide R4 and R3 to do that, to actually get IX. And that's going to be shown here. I'm going to redraw the circuit again. Still have our 10 ohm resistor. 3. There's our 3 up here. Resistors are getting a little bit messy. IS. And then we can also say, if it helps, that 5 amps is going, we know 5 amps is going through this resistor here. And that is because these total currents, this current, these currents going here, and this have to add up to the current flowing into the going into that node, and that's something we'll talk about more with KCL. We'll talk about those laws. So we know 5 amps are coming through here, and then 5 amps is going up from here through both of these combined. So let's finish writing our resistor values. R3 and R4 are both 30. Now I know because both of these resistances are equal that the current is going to be divided evenly. So I can from here say that IX is going to be equal to half of 5, which is 2.5. But just to show how we're getting there, we're now working with the parallel combination of 30 and 30. So so this was R4. Yeah, this was R4. R4 is equal to that. The current that is being divided is now 5 amps. Our total resistance between this, using product over sum, is, or just the basic rule, is 15 ohms. And the resistance that we're actually interested in is 30. So this is just going to come out to be half of 5. R4 equals 2.5 amps. And then, like I said before, all this current here is going to combine and then flow back through this 15 ohm resistor down here. So that's how we solve that problem, just using current division only. And later on, we're going to talk about KCL. So hopefully these nodes and meshes and everything make sense later. So thanks. And also, just to verify our results from that previous example, I went ahead and drafted it up in LT Spice and to run our operating point. So for R5, we see we're getting 2.5 amps, and for R3, we're getting 2.5 amps through it, which corresponds to the answers that we were getting before. sometimes in LT Spice, when you have the resistor terminals flipped the opposite way, it changes the sign on the current, but we're getting the same values, and we know that the current is flowing the right way in our answers, and so that's what's important. So that's just the verification of that.